So I'd like to take a look at another triple integral. This one's going to turn out to work really well if you use cylindrical coordinates. So generally you write dv here over the region E. The region E, or the solid region E, is the region that is above the xy plane contained within this cylinder. The cylinder's equation is x squared plus y squared equals 5. So that's that equation we've graphed. And below this paraboloid, which is up here, which I'll trace over in red. Bad tracing, sorry. But you can see now that there's this region between them, this cylinder with this paraboloid sort of cut out of it. So we're going to integrate over that entire 3D region. And the reason this one works so well in cylindrical coordinates is because you can clearly see z is bounded from below always by this disk, this purple disk here, and from above always by the paraboloid. So it gives you two nice easy ways to bound z. So z goes from 0 to 1 plus x squared plus y squared, which, by the way, if we're going to use cylindrical coordinates, is really 1 plus r squared, because of Pythagorean theorem, x squared plus y squared equals the radius squared. All right, so let's go take this integral now and rewrite it for ourselves. So here we go. Triple integral. E to the z will stay that way. Don't forget you need a correction factor of r when doing an integral in cylindrical coordinates. I'm going to integrate with respect to z first, then theta, then r. And you can see some really nice show up here, actually. So let's take a look. Here's our limits of integration for z. Theta is going to go from 0 to 2 pi, so we're going to go all the way around that cylinder. And then r is going to go from 0, and be careful here. The equation of this circle is x squared plus y squared equals 5. That means that the radius is the square root of 5. So this could be a square root of 5 here. Okay, one at a time. Here we go. So the first integral with respect to z. This thing in here has no z's in it. Oh, I'm sorry, it does. That's got an e to the z, and the antiderivative of e to the z is just that, e to the z. It's being multiplied by some constant r. And we're going to evaluate that from 0 to 1 plus r squared. So if we plug in 1 plus r squared, we get r e to the 1 plus r squared minus, we plug in 0 for z, we get e to the 0, which is just 1, so r times 1. So that's pretty nice, actually. It turns out this is really special. You'll see why in a couple more integrals. Now we're going to integrate with respect to theta from 0 to 2 pi d theta. So that's what's going to happen here. This whole thing from 0 to 2 pi d theta. Turns out this is not a lot of work because there's no thetas in here. So this is just a constant. So the antiderivative is r e to the 1 plus r squared minus r times theta evaluated from 0 to 2 pi. Now we plug in 2 pi, it's just that. If we plug in 0, the term drops away. So luckily, we just get this, r e to the 1 plus r squared minus r times 2 theta. So I'm going to keep that as a constant on the outside. I'm going to do the last integral, which is the integral from 0 to square root of 5 dr, that last one. So let's do that. Integral 0 to square root of 5. Don't forget the 2 pi. That's coming from over here. And dr. So this is really two separate integrals. This one's easy. This is just minus a half r squared. This is the one where you really got to think carefully about it. But what you realize is that the antiderivative of e to the something is always e to that exponent. And what I like to do is think, okay, if I took the derivative of this thing, what would I get? I would get e to the 1 plus r squared and then times 2r because of chain rule. We multiply by the derivative of the exponent. And what you'll notice is up here, we have the r, but we're missing the 2. So there should have been a 2 here to match this perfectly, right? And it's missing. So what does that mean? Well, it means that there must have been a 1/2 in front of this. There must have been a 1/2 here. So our antiderivative is really 1/2 e to the 1 plus r squared minus 1/2 r squared. And we're going to evaluate this from 0 to rad 5. And when we're all done, we have to multiply by that 2 pi. Can't forget about that constant. So let's do this. We plug in rad 5. We get 1/2 of e to the 6th power minus, if we plug in rad 5 here, we get basically 5/2, right? And then we do minus what happens when we plug in 0. So we would get 1/2 e to the 1, which is just e, minus 1/2 times 0 squared, which is 0. So there you have it. And then we have the times 2 pi, which we won't forget about. So the final answer is going to be 2 pi times, if we simplify this at all, there's not much to do really. You get 1/2 e to the 6th minus 5/2 minus 1/2 of e. For 1, I guess you could distribute that 2 pi. So you end up with pi e to the 6th minus 5 minus e. And that would be your answer. Okay, great. Thanks for watching.